Hello students, today I am going to explain you a little bit about the Mollier chart. The Mollier chart is also called HS chart as well. So this is very much useful in solving the steam related problems and heat transfer problems, mainly wherever the interaction of steam with certain machines like turbines, nozzles or compressors or engines, steam engines. So where steam is used as a medium to run those engineering equipments. So the steam properties needs to be understood, and then accordingly we have to calculate things like enthalpy, entropy, and the quality of steams, things like that we need to calculate. So for that purpose the Mollier chart is very useful to calculate those things. So first let's understand the Mollier chart, how it is. So as you can see, this is the Mollier chart, and here on the abscissa you have the specific entropy. So on the x-axis you have specific entropy, and that is represented by symbol S. So S is the symbol for specific entropy, and the units will be obviously kilojoules per kg degree Kelvin. So on the x-axis you have specific entropy. Similarly, on the y-axis, that is ordinate, you have specific enthalpy. So specific enthalpy, the symbol is H, and it is the units for that. The units will be kilojoules per kg. So because specific enthalpy is itself is a type of energy, so you can also say that it is one of the important thermodynamic potentials. So enthalpy H, and as you know, enthalpy H is a sum of internal energy and the product of pressure and volume. So that is H is equal to U plus PV. So anyhow, the specific enthalpy is represented along the y-axis of this Mollier chart. So as you can see that specific enthalpy is starting at around 1700 kilojoules per kg, and the entropy is starting at about 5 kilojoules per kg degree Kelvin. So as you move along the x-axis, the entropy will be increasing by approximately about 0.2 kilojoules per kg degree Kelvin, and along the y-axis if you go upwards, the enthalpy will be increasing by about 100 per each unit. So basically apart from this is how it is called HS diagram as well, because H is on the y-axis and S is on the x-axis. So the Mollier chart is also called as HS diagram sometimes. Okay, so besides these two things, important things we need to study about this is there is a dry saturated line, which you can see that dark black line here. So that is called the saturation line. So that means above this line everything will be superheated steam, and below this line will be wet steam. So and exactly on that line will be dry saturated steam. So if I am looking for any point below this line, obviously it will have a property of wet steam, so it will have some kind of quality in it. So the quality of steam is represented by dryness fraction. So you can see that for all the wet steams below this dry saturated line, all the wet steams will have a thing called dryness fraction. So as you can see that these lines, curved lines along parallel to the dry saturated line, you have curved lines. So these curved lines are called constant dry fraction lines, which other words these are called the dryness fraction lines also. So dryness fraction is represented by X. Generally while solving the problems we denote it by X. So as you can see that X is starting from 0.7 onwards, 0.75, 0.8, 0.85, 0.9 and 0.95, and finally it reaches to 1. When the value of X becomes 1, that means it is a completely dry steam, dry saturated steam. So anything below that is a wet steam. So obviously for wet steam it will have X is equal to something, whether it may be a 0.8, 0.9, anything between 0.7 to 0.1 or sometimes below that also. So anything on that line will be X is equal to 1. Anything on the any steam which is on the dry saturated line, for that the X will be taken as 1 because there is no wet in that. So generally dryness fraction is represents the amount of wet steam in the given total volume of steam, total mass of steam. So that's why dryness fraction applies to only wet steam only. So this is about the dryness fraction lines which are parallel to the curved line of dry saturated line. Now coming to the other part of this Mollier chart is the important property we can see here is the pressure of the stream. So the pressure, constant pressure lines, you can see that these inclined lines are representing the pressure. Rather, the pressure is represented by these inclined lines. So as you can see that pressure is starting from somewhere 0.06, 0.05, 0.1, 0.2, 0.3, 0.4, 0.5, 1.5, 2, 2.53, like that the pressure is increasing. Here you can see that 8 bar. So all these are pressure is represented in units bar. So as you know, 1 bar is equal to 10 to the power of 5 newtons per meter square. So each of these pressure lines, constant pressure lines, are representing certain amount of pressure in bar. So here the pressure is, this line represent the 8 bar pressure line. So any point on this particular line will have a pressure of 8 bar only, because this is a constant pressure line of 8 bar. Similarly, if you take this line, the constant pressure line of 20 bar, this is because this line is representing 20 bar. So any point on this particular line will have pressure of steam as 20 bar. So that way the pressure goes on increasing and it reaches to certain point. Even it can be taken as 1000 bar also. The maximum pressure we can represent is 1000 bar on this particular graph. So these are the constant pressure lines which are kind of inclined along the y-axis. Now coming to other important property which we can read from this Mollier chart is constant temperature, the temperature of steam. So you can see that there are these horizontal lines, slightly inclined horizontal lines. These are called constant temperature lines. So any point on this particular curve, horizontal curve, represent the same temperature. Suppose for example, if you take this particular line, it has 400 degrees centigrade. That means any point on this line represents 400 degrees temperature of the steam. So if I have a particular point, a steam is falling on this particular line, that means the steam will have 400 degrees centigrade. So now that is the constant temperature lines which are horizontally inclined lines. So that's way we can read the temperature of a given steam from the Mollier chart. So apart from that, another important property we can read from Mollier chart is the specific volume. So as you can see that there is little bit inclined to pressure lines or the constant volume lines, constant specific volume lines. That means any point on this particular line is having same specific volume. So for example, if you see this particular dotted lines, of course the specific volume lines are dashed lines. So unlike the constant pressure lines, the constant pressure lines will have dark line, thick line, whereas specific volume lines are represented by dotted lines. So specific volume on this particular dotted line will be about 0.02 meter cube per kg. So as you can see that specific volume will be increasing as you come down. So at this particular dotted line, the specific volume is about 0.7, whereas if you see here it is 0.02. That means the specific volume is increasing in this direction. So this is the another important property which we can read from the Mollier chart, that is specific volume. So how it is going to help the Mollier chart in solving steam problems? Let's take one example of a property of steam before entering the turbine. So let us say that a turbine is entering at 15 bar and at a temperature of 250 degrees. So what happens is we can find the enthalpy of that particular steam at the entrance of steam turbine by knowing the intersection of these two things. that is 15 bar intersection, 15 bar pressure and 250 degrees centigrade. So wherever these two are intersecting, this particular point becomes the first point, that is the point of entering the steam turbine. So here if you see, the enthalpy of steam can be read along the horizontal if you draw a horizontal line from this point, you can see that it has some specific enthalpy. So the specific enthalpy roughly about this point is 2910 kilojoules per kg. So this way we can know that if I know the pressure and temperature of the steam before entering the turbine, I can say that the steam has this much enthalpy before entering the turbine. So H1, that will be 2910 kilojoules per second kg. Now we can also say that suppose after expansion in the turbine, obviously the enthalpy will drop, the temperature also will drop, the pressure also will drop. So let us consider the second point as a 4 bar and the 4 bar and temperature of, let us say 150 degrees. So what happens is, this is the second point. So 4 bar and 150 degrees are intersecting at this particular point. So if I look horizontally at this point, I can say that roughly about the enthalpy is about 2760 kilojoules per kg. So that becomes my enthalpy at the exit of the turbine. So I have the enthalpy at entrance, enthalpy at the exit. So the difference of these two enthalpies is nothing but the work done. You can say that the turbine has generated this much amount of work by calculating the difference of enthalpies. So what I am doing in this chart is, I am able to find out the enthalpies at any given two different points. At the same time, we can also see how much entropy is there at this point. So I can also say that the entropy is, if you look the entropy for vertically from this point, I can see that the entropy is something like 6.7 or not even 6.7, 6.665. So that is the way I can read the entropy at any given point, by looking vertically down where it intersects at the x-axis. So if I draw a vertical line from any point on the Mollier chart, it will give me the entropy at that particular point. So I can also see what is the entropy at the second point. So generally speaking, the turbine expansion will be isentropic expansion, so we can assume that the entropy will remain same. So generally that is the ideal case scenario. The entropy will remain constant while expanding in the turbine. So that leave aside, but generally speaking, how to read the entropy is what we are discussing here. Also assume that after expansion the steam has come to certain point here. So I can know that by looking at this inclined curved line, I can say that the quality of steam is this much dryness fraction. So I can say that at this point the dryness fraction is about this hard line representing 0.9. So that means 0.91 is my dryness fraction. X is equal to 0.91 at this point. So this is another advantage. By looking at Mollier chart, I can tell that my steam has the dryness fraction of X is equal to something. So here X is approximately about 0.91. Similarly, I can also know what is the volume, specific volume of steam at this point, because at this point you can see that these are the dashed lines. The dashed line represents the specific volume. So this specific volume line is about 0. You can say that. So my specific volume is 0.05. So this specific volume is about 0.05, and this like that I can say. So this is the another specific volume line. So you can also say that this is about 0.09. So by approximately, by looking at this particular point, by dividing equally between these 2 points, and approximately we can know what is the specific volume of this particular point. So that way we can understand initial specific volume and final specific volume, and by subtracting these two we can say that what is the change in volume of steam. So all these properties we are reading is for the steam at any given point, whether it is before turbine or after turbine, before nozzle or after nozzle. Whatever we are reading from this Mollier chart, those are nothing but the properties of steam. All the properties can be read from the steam. Even for example, if you want to calculate the velocity of a steam through the nozzle, so we can find out by using the formula V is equal to under root of 2 into H1 minus H2. So if you know the H1 and H2, you can easily calculate the velocity of the steam. So Mollier chart helps us in this way to calculate quickly the things, enthalpy, entropy, and from those two things we can calculate the work done in case of steam turbine, or velocity in case of nozzle. Many other applications also we can solve the property of steam problems using this Mollier chart. Thank you.